We're going to see a new way that two functions can interact, and it's called the convolution. The convolution of f and g is denoted by f asterisk g, or f star g, and it is the integral from 0 to t of f of tau times g of t minus tau d tau. That variable is the Greek letter tau. And since we're integrating with respect to tau and then substituting for tau 0 and t for the lower and upper limits of integration, the result is a function of t. It can be shown that f star g is equal to g star f. In other words, convolution is commutative. What that really means for us is when we see this integrand here with the f of tau and the g of t minus tau, it doesn't matter which of f or g has the t minus tau in it. Let's see what this actually looks like here. We're going to find the convolution of the cosine of 2t and e to the t. By that definition, it is the integral from 0 to t of the cosine of 2 tau times e to the t minus tau d tau. If you wanted to explore a little bit, you could do this as the cosine of 2 times the quantity of t minus tau and then e to the tau. And you see you'll get the same answer I'm about to get. Well, this is going to be integration by parts, and we have a product of a cosine and an exponential, so it's going to take 2 rounds. Let's see if we can do this a little bit quickly here. Setting u as the cosine of 2 tau and dv as e to the t minus tau d tau, I'm going to also relabel the integral. I'm going to call it I, and I is going to equal negative e to the t minus tau times the cosine of 2 tau, and that's going to be evaluated from 0 to t. And I'm going to write the next integral as plus the integral from 0 to t of negative 2 times the sine of 2 tau e to the t minus tau d tau. Another round of integration by parts using u equals negative 2 times the sine of 2 tau, and dv is e to the negative t minus tau d tau. And evaluating the first expression at its upper and lower limits of integration is going to give us I equals negative cosine of 2t plus e to the t, and then from the integration by parts formula, plus 2 times the sine of 2 tau e to the t minus tau. That'll be evaluated from 0 to t, minus 4 times the integral from 0 to t of the cosine of 2t e to the t minus tau d tau, thereby repeating the integral that we started out with. Collecting like terms, so adding 4 times the integral to both sides is going to give us 5 times that integral on the left, and on the right hand side I'll rewrite e to the t minus the cosine of 2t, and then evaluating the expression with the sine and the exponential at its limits of integration is going to give us plus 2 times the sine of 2t, finally giving us that the integral is 1/5 e to the t minus 1/5 cosine of 2t plus 2/5 times the sine of 2t, and that's what we can write down as the convolution of the cosine of 2t and e to the t. Next, we're going to continue the thought by finding the Laplace transform of that convolution. Well, it's the Laplace transform of that 1/5 e to the t minus 1/5 cosine of 2t plus 2/5 times the sine of 2t. We'll transform these one by one, but also we'll note that there's a factor of 1/5 everywhere. So I'm going to write that 1/5 out front. And the transform of e to the t is 1 over s minus 1. The transform of cosine of 2t, cosine is going to give us an s in the numerator. 2t tells me that k is 2, so s over s squared plus 4. And then for the sine, I only factored out 1/5, so we have a factor of 2 here. And then remember, the sine has k in the numerator over s squared plus k squared, so that's going to give us a 4 over s squared plus 4. Getting common denominators is going to give us s squared plus 4 plus a negative s plus 4 times s minus 1 all over s minus 1 times s squared plus 4. This is going to give us 1/5 times 5s over that denominator of s minus 1 times s squared plus 4. The 5 divides out, and reversing the factors in the denominator is going to give us s over s squared plus 4 times 1 over s minus 1, which you might recognize as the Laplace transform of the cosine of 2t times the Laplace transform of e to the t. What we just found is the Laplace transform of the convolution of the cosine of 2t and e to the t is the product of their transforms. This is not a fluke, and it's actually supported by the next theorem, which is called the Convolution Theorem. If f of t and g of t are piecewise continuous on 0 to infinity and of exponential order, then the Laplace transform of the convolution of f and g is the product of their transforms. We'll even prove it. The Laplace transform of the convolution of f with g is equal to... Now, the Laplace transform is defined as an integral from 0 to infinity e to the negative st times dt. The thing we're transforming is the convolution of f and g, which itself is an integral from 0 to t of f of tau g of t minus tau d tau. Now, if that doesn't look weird enough, we're actually going to bring in the unit step function, because note that the unit step function of t minus tau is equal to, remember, the unit step function is 0 and then 1, right? It's 0 as long as t is between 0 and tau, and then 1 if t is greater than or equal to tau. What that means is that the unit step function of t minus tau is equal to 0 if tau is bigger than t. Trying to think about this too hard will twist your noodle, but look, if tau is bigger than t, then u of t minus tau is 0. That means that we can rewrite the convolution integral. First, I'm going to rewrite the transform integral from 0 to infinity e to the negative st, and then the convolution integral can be written as the integral from 0 to infinity, because for values of tau bigger than t, that's 0, times f of tau g of t minus tau u of t minus tau. The convolution integral is with respect to tau, and the transform integral is with respect to t. Now that we have both integrals with limits going from 0 to infinity, we can reverse the order of integration, well, without having to mess with the limits. So we're going to write down the convolution integral first from 0 to infinity f of tau, and that'll be with respect to tau, but inside of that we have the transform integral from 0 to infinity e to the negative st g of t minus tau u of t minus tau, ran out of room there, with respect to t. Now look closely at the transform integral. We've got the integral from 0 to infinity e to the negative st g of t minus tau u of t minus tau dt. Well, that's the Laplace transform of g of t minus tau times u of t minus tau. So that part can be replaced. The transform of u of t minus tau is going to be e to the negative s tau. The transform of g of t minus tau is g of s, because those arguments matched. Now that's still inside what I've written as the blue convolution integral from 0 to infinity of f of tau d tau. The g of s can come out because that's constant with respect to tau. What's left is the integral from 0 to infinity of f of tau times e to the negative s tau d tau, which has the exact form of the transform of f. And so the result is g of s times f of s as promised. And now we're going to put this into action. Find the Laplace transform of the convolution of t cubed and t times the sine of 3t. According to what we just saw, this is the transform of t cubed times the transform of t times the sine of 3t. Now remember that t in there is going to be the negative derivative with respect to s of f of s. So this is going to give us 6 over s to the 4th power for the transform of t cubed times the negative derivative with respect to s of the transform of the sine of 3t, that transform being 3 over s squared plus 9. After differentiating and simplifying, you'll find that this is 36 divided by s cubed times the quantity of s squared plus 9 squared. I encourage you to get to that point on your own as well. The next two actually present us integrals. The Laplace transform of the integral from 0 to t of the sine of tau times the cosine of t minus tau d tau. Well, that's just the convolution of the sine and the cosine, and so the Laplace transform is the product of the transform of the sine and the transform of the cosine. That turns out to be s over s squared plus 1, the quantity squared. We'll save the other example you see on the screen for the next video.